Hey everybody, it's Mr. Kramer again, and today I'm just going to be going over what we have in front of us, the Lightbending 301 assignment. Now, if you haven't yet watched the part of the stream last week where I go over ray diagrams, it's sort of optional. However, it will make everything you do beyond this point make a lot more sense. So I have it linked inside the assignment description if you were kind of ahead of the curve and didn't get to this assignment description until now. Or got to it before now, go back and maybe watch this. You can maybe watch a double speed or something or cut around, especially if there's a part that you don't understand. You can jump to the part that matters. However, if you're just opening the assignment, you were brought to Lightbending 301, which is the third and final installment of using refraction, reflection, and diffraction. Primarily, we're going to be using reflection for mirrors and refraction for lenses. So primarily, we're just going to be asking questions: how do mirrors, how do lenses work? Is there a pattern to how they behave? And if so, can we name what that pattern is? And make predictions. So mirrors are cool, especially curved mirrors. And lenses are definitely cool. I mean, I have some on my face right now that help to concentrate light into the back of my retinas so that it's in focus as opposed to not in focus. There's also lenses inside my eyeball that do the same thing. So we got a lot going on. Actually, there's a pair of lenses, I believe, in any glasses lens. But anyway, so there starts with some review questions. I'm not going to go over these because these, I'm mostly just trying to make sure that people understand how to use the simulation. So you can scroll down. I would suggest you read through all of this. If you don't like reading, maybe perhaps watch the video that I put out. I especially go through the difference between convex and concave lenses. And I talk about the idea that convex lenses are converging lenses and the parallel rays from a distance will come to a focus point. And a concave lens does the opposite, where parallel rays will essentially diverge from, or in this way, will diverge from a focal point, and you'll get an imaginary image here. So there's two main kinds of lenses: converging, diverging, and we're going to look at both. Now, there's a formula here for magnification. Now, we all know that lenses can be used to help magnify things, both in glasses or if you've ever used a magnifying glass. So magnification is defined as two different ratios. So either the ratio of the height, so this is the magnification, it's a ratio, which means it's not going to have any dimensions, and it's going to be basically a percent, but without the percent sign. So like where the number 1 is 100%, and the number 0.5 would be 50%. So if the height of the image is divided by the height of the original object, that'll give you the ratio. Alternatively, the distance that the image is from the lens divided by the distance of the original object from the lens, that's also going to give you the magnification ratio, I believe. There was a typo in this earlier. I think that this originally had HO over HI, so you may need to fix this if you already made a copy of your own. Okay, next it takes to the simulation. So you click on this link, it brings you to this website. Now you might notice that this is kind of small. I can full screen it, which is probably what we'll do for now, but you can also click and drag it to just make it a little bit bigger. Can I just drag it this way? No. Which maybe makes it easier. Which maybe makes it easier to tab back and forth. That's maybe a little bit too big. What the heck is up with this thing? Okay, here we go. To-do! We're here. So what I have here is an image. I have a candle. You could start with an arrow, like if we did the ray drawing diagrams that I did. If you watched the previous video, we used an arrow. An arrow is over here. This is the object. Its distance from the lens, well, that's the object distance here, which is 56 centimeters. So it's measuring 56 centimeters here. And then the object height is 10 centimeters. If I want to make the height bigger, I can drag this. So see how the height is moving up and down. Oh, now it's twice as big, 20 centimeters. And then whereas the distance hasn't changed, and if I want to change the distance, how close this is, I can just slide it left and right. So it was whatever it was, 50, and then I can make it, 9. So that's the object distance and height. And then the image distance and height, is going to depend on how the lens is behaving. So if I have the if I have the object distance and the object height set how I want it, then the only thing I can do to change sort of how the lens behaves is to shrink or lengthen the focus. And you'll notice it's not doing anything to the actual object because the object isn't changing, but it is changing where that image of this object will appear on the opposite side. So how far away the image distance is. And then the image height, again, it'll tell you how big the image is, regardless of how big the original object was. Okay, so I was supposed to not change anything. So, whoops. So he says set up an example. Okay, here we go. Set up an example. So we're going to go through one together. So what is the focal length? 20 centimeters. So I'm going to set the focal length to 20 centimeters, which I messed up, but hopefully I can get it to exactly 20. I cannot. I'm going to have to reset this page. Beep, beep, beep. Okay, here we go. Okay, focal length is 20 centimeters. What's the object location and height? So the object location is 43.8. Oh, actually, he has it set to this. So I have to set it to 78.5. 78.5. 78.5-ish. Okay, well, close enough. So here we have the object very far away from the focus. Notice the 2f is an important sort of indication here. So the f is the focal length. If you watched my previous video, you saw that a lot. The 2f is kind of a turning point in some behavior, and so it's often noted as well. For mirrors, it's also called the radius of curvature, but we'll get to that. Okay, and the height is 10 centimeters, which mine is also set at. So here we go, 78 centimeters and height 10 centimeters. What's the image location? Well, the image is on the other side, so it's got a distance of 27.2. Now, that's quite a bit closer to the mirror than this is, so it's not quite as far away from the mirror. And then its height is negative 3.4 centimeters. So it's negative because it's flipped over. You can see this arrow is pointing up, but this arrow is pointing down. It's kind of small on your screen, but it is pointing down. So there we go. Then the magnification should be HO. This is kind of messed up, isn't it? Object. It should be the image over the object, I believe. It makes a lot more sense to me. So this might be wrong as well. Let me check. Image height. Yeah. So this should be the other way around, and this is kind of what I'm here to fix because I was told this was wrong, and then now I'm fixing it. Hooray! So this should be the other way around. Magnification is negative 3.4 over 10, and so I got to use a calculator. Negative 3.4 divided by 10. I didn't really have to use a calculator because it's negative 0.34. 0.34, which means that basically the image is 34%. This essentially means image is 34% of object and upside down. Does it make sense? So hopefully that interpretation of this number, negative 0.34, makes sense to you. And then it says to calculate the magnification this other way, and this is probably also flipped upside down. So instead of, this was supposed to be HI over HO. And I apologize this was not right the first time around. And then this should be the distances divided, but it should have the smaller distance on top. Yeah, so again, it should be, oh no, this is correct. Yeah, image. Okay, so then it should be the distance of the image, which is 27.2 over 78.2. So if I flip this around, 27.2 2 divided by 78.2. And I go into my calculator, copying this. Oops, Control Z. Don't want that. Bam. Bam. Gives me 0.347. Oops. Which is pretty similar to what I got before. Negative 0.347. Oh, shoot. One of these needs to be negative. Oh, interesting. Distance I. Oh, so negative I is one of the distances. Okay, so okay, sure. So then this should be negative on top, and then this will be whatever I got for my calculator. 3.347. And again, that's the same thing I had before. Negative 3.4, negative 3.4. So it should be, these should give you the same answer, which is kind of surprising. The fact that the distance that the image is scaled, that ratio, is the same as the height being scaled. I mean, it doesn't seem unreasonable, but for it to always be true, that's a pretty strong statement. So we're going to use that information later in this magnification equation to do everything else we need to do. Sorry that these equations were a little bit wrong and I was double checking everything. It's just, it was not right before because it was finding the inverse of the magnification as opposed to magnification, and it's just the way it is. So it's fixed now. If you're watching this video and you haven't done it yet, then it'll be right when you see this document. Okay, so again, this is the same thing. So the image is 34.7% the size, which is smaller, and upside down. All right. So here's a chart for this example. So 20 centimeters, we said it was far outside, so beyond 2 times f. So if f is 20, 2 times f would be 40. And so farther than 40 would be far outside. So 78 is bigger than 40. The height was 10, and then we found this magnification, and this is all wrong. So now I got to copy the right things in here. Oh, hold on, we'll get this right. I want this. Ta-da. And then I want this other thing that I found. Bam. Get rid of the M there. Okay. Now the image is real. Sorry, the image is real. Oh, right. So the image is real. This isn't saying that, this should be a little bit deeper. The image is real as opposed to virtual because this image, if you go back to the simulation, this light is actually appearing here. It's being bent and being concentrated here. This is a convex mirror, converging mirror. So it's converging to this point and it's real. If it was diverging from a point, and we'll get to that later, then it would be imaginary. And then the image is obviously smaller. This arrow is quite a bit smaller than that. So that's basically how you use a simulation. You set up the pre-case that we want, so the distance we want. In this case, we wanted to be, this is the 2f. We wanted to be further outside than that. You can adjust the height if you'd like to. And then you read off this data, and you can use the ratio of the heights or the ratio of the distances, which are the same. It looks like I was lagging there. So you can use the ratio of the heights or the ratio of the distances to find the magnification, which is, some percentage basically. Okay, so next, let's say you wanted to do it exactly at 2f. So you would need to go ahead, that's what this thing is saying. So if the focus is still, let's keep the focus the same, 20. If I want to put exactly at 2f, then what number do I need it to be at? Well, 40, or as close to 40 as I can get it. So then this will be, so at 2f, of course, this means I want this at 40. So I'd put in 40 here. Maybe I'll do this example. 40 centimeters. Okay, so what's the distance of the image? Well, the image distance is also 40, which is confusing. 40 centimeters. What's the height of the object? Well, the object height is 14.1. And then the height of the image is negative. Again, it's not quite 14.1 because this thing is, but it's basically the same height. So negative 13.9. Maybe I should put in the actual distance here, 40.4. 40.4. There we go. Now, if I do the ratio of the magnification using the heights, so I'll do 14.1 divided by 13.9. Those are very close to the same number. So 14.1 divided by 13.9. That gives me 1.01. So 1.01, actually it's negative 1.01. So it is flipped upside down. That's the negative. And the 1.01 means that this is basically 101%. So it's been a 1% magnification, but flipped. And then if we do the same thing with the distances, we should see the same thing. So again, 40.4 divided by 40. Is this wrong again in all these tables? Well, I'll just do it correctly. 40.4 divided by 40, and this was 14.1 divided by 13.9 equals, there we go. And this equals this, well, probably something similar. We'll see here. 40.4 divided by, here we go. 40.4 divided by 40. 1.01. So it's the same thing, or very close. So as you can see, oh, again, negative on that one. So negative again. So it's flipped upside down. This is again a real image. So I should be highlighting. My text. Bam, highlighted. And then in this case, the image isn't larger or smaller. It's neither of them. So I would say same size. Maybe I just wouldn't highlight either of them to indicate that it's the same size. Or highlight both of them. Does the same thing. Oops. So let's highlight both. Highlight. Bam. Highlighting. So cool. Okay, so that's how you do it, and then it says take a screenshot of the setup here. So here I'll go in here. I'll go to I'll magnify, and then I'll hit my print screen button. Print screen. And then I hit escape, and then I go in here, and then I put in here, and I say, here we go. Bam, Control V. Oh, and it's going to give me my stream setup and stuff on one monitor. But for you, it won't do that because you'll probably only have one monitor. So it won't be a problem. I could probably crop this if I wanted to. Yeah, crop image. So get rid of that other screen. Actually, get rid of all this other stuff. Don't need that. Don't need that. Don't need that. Bam. And then this will be a little bit easier to see. Beautiful. So now you got it. Now you can put the screen setup and you can see everything there. So that's another thing you're gonna need to do for this assignment. So I can continue going on, but it's all the same. So if I want to do between 2F and F, what that means is, so right here, I go back to my simulation and I bring the arrow between the two. Doesn't exactly matter where between. Let's say I put it here. Then I say, oh, that's the object distance, object height, image distance, image height. So you put it into the equation. I'm going to fix these tables after I cut from this to make sure that everything is correct, but the equations will be right everywhere you see them, as opposed to right now where they're kind of messed up in places. So that should be good. And then trying to generalize, well, this is important. When the distance of the object is much greater, what happens, what happens? As it approaches, what happens, what happens? As it approaches the single focus distance, what happens, what happens? So you need to be putting descriptions exactly where these are. So for the one we just did, when we were much greater than the DI was shorter, was smaller, and the height was smaller and flipped. Oops, and flipped. And then at exactly this, the DI was the same, and the height was the same but flipped. So you need to take your data and put it into these summary statements. Okay, so that's that. I'm going to delete this now so that it's pristine. Now you're going to do the same thing but diverging lenses. So up here in the front, you can click diverging. Up here on top, you can click diverging. Aha, there it is. And you're going to start again from far away, go medium, between, at the focus, closer than the focus. And you should see something different in this case. So maybe I'll do one example just to go over it, and that'll probably be the end of the video. So let's do far outside 2f. So I'm going to go out here again. Here I'm at 68.5. So 68. The focal distance is still 20, I believe. 20 cm. Yep. Far outside. So I did 68.5. Okay, what's the distance of the object? So the object is 68.5, but the image is 15.3. 15.3. The height of the object is 14.1, but the height of the image is 3.2. Notice that's positive 3.2 because this image isn't upside down. It's actually right side up. It's shrunk. It's also on the near side of the lens, which I believe causes this distance to more accurately be measured negatively. Because we expect the image to be on the far side of the lens. So this is actually what we would call a positive image distance. But then because it showed up on the other side of the lens, it's actually what we call a negative distance. So even though on here it shows it positive, that I believe that is inaccurate. But we'll go ahead and we'll show once we do the equation. So now we're going to do the heights. So we do the height of the image over the object. So again, this is wrong, but I'll fix it. So we're going to do the image of the object. So 3.2 divided by 14.1. Notice that there's no negative signs here because nothing's been flipped. 3.2 divided by 14.1. And that gives me 0.226 or 0.223. 0.2 or 0.23. So again, this 0.23 means a 23%. So the image is only 23% the size of, or 1/4 the size of the original object. And because it's a positive number, it hasn't been flipped. Let's do the same thing but using the distance to calculate our magnification and see if we get the same thing. So just looking at the distances, my original distance was 68.5. So this equals 68.5 divided by, so again, this says put the negative distance of the, oh, I did it wrong, my bad. Let's do it correctly. The distance of the image first, so 15.3. So di is the distance of the image. So 15.3. Uh-oh. My mic, my speakers. Okay, we're good. 15.3. Now, normally, it's supposed to be negative. But I already said, see the negative sign up there? But I already said that this was negative. I recorded this as negative 15.3. So this is really negative 15.3 divided by the distance of the original object, which is 68.5. Okay, all this to say, this negative and negative cancel out, so this should give me a positive number. I'm going to divide these two in my calculator. So just going to copy paste here, get rid of that parentheses I don't need. And it gives me, again, 0.2. It doesn't give me 0.23, it gives me 0.22, but something very close. Equals, let me do it like this, equals 0.223. So again, I'm getting something that's very close to this magnification ratio of 0.23, 0.223. No matter how I calculate it, I should get something very, very close to the same answer. This image is not real. This image is virtual. Bam. Oh, I should be highlighting my final answers too, because I'm a good student. This image is virtual because, as you can see, the real rays of light are all converging in these different directions. But the actual image is back here, essentially where those rays of light are diverging from. So if you imagine this ray, and this ray, where they all join up, well, it's right about at this point here where the imaginary image is. And then, of course, in this case, the image was much, much smaller. So that's an example of how to use a concave or a diverging lens. So, man, Yeah, okay. My speakers are kind of acting up. But so that's that. When you get down to you're going to do the same thing. So we just did this example. The distance was actually negative and smaller. So it was on the same side of the mirror, but it was closer to it. The distance was smaller. And the height was smaller, but still positive. So you'll go through for all of the examples you do. This kind of takes a while, which is why I gave you 2 weeks to complete this assignment. So, oops. So that's that. Okay. I think if you want to, I'll go into mirrors on a following week. But I think for now, this should be enough to get you going. If you want to do mirrors on this, you just click the lens button and change it to mirrors. You're going to do similar stuff. Different behavior, but same process. So best of luck with all of this. If you have other questions, let me know. I'll be sure to fix the assignment so that all of the formulas are correct and you don't get confused which number you're supposed to be dividing. But with that, I'll catch you later. And go. All right, hey everyone. This is a really short demonstration just showing off a bit of a contraption I've put together just to demonstrate air pressure. So what I have here is a plastic tube. And at the end of one end, I've tied a balloon. So here's a little balloon tied to one end, and the other end is open to the air. Now, after I blew up the balloon, I filled up this tube with some water with some food coloring in it, which you can see. Now, you might notice that the food coloring water is only going up to, they're going up to different heights on one side. So on the side that's open up to the air, it's all the way up here. But on this side next to the balloon, it's all the way down here. So there's a pretty big difference in height, and if I rotate this, you'll see that that difference in height actually is maintained. So what that's telling us is actually that there's a difference in pressure between the balloon and the outside air, which is not all that surprising because we know this balloon has, you know, it's blown up a little bit, so there's a little bit of pressure in there. That difference in height is actually directly proportional to the difference in pressure. Now what I want to show you is that as I squeeze this balloon, I'm going to be decreasing the volume. What that's going to do is it's going to decrease the volume inside this container, which is going to essentially try to increase the pressure. But that increase in pressure is going to push this water out the tube and up the other side. So you'll see a difference here. As I squeeze this, the water level goes up just a little bit. Just squeezing it, and I let it go down, and it goes back to normal. Squeeze it again, goes back up. Squeeze it, goes down the other way. If I were to blow air into this tube on this side, you could also see the water go down a little bit. Until I got them till they were about even. I could also suck on this tube and suck up the water just like a straw. I'm not going to put it into my mouth because it's gross. And then the last thing that I wanted to do was to pop the balloon, but I'm not sure I've actually... Aha, there it is. So with the balloon popped, then you can see that the tube now, the level of the water has returned to where they're both even. So that's all I wanted to say. Have a good one.